So rather than prove that theorem, the proof is in the book, and the only part that I want you to think about when reading that proof is the separation into the singular part by the Laurent series and the bounding of everything else by Cauchy's integral formula. But the tools are there, and learning a proof actually works better when you read. So I'm going to let you do that. I'm going to go over an example of the use of the lemma. And the example of the use of the lemma is we're going to do the principal value of the integral of e to the ix over x, where x ranges from minus infinity to plus infinity. So this is a principal value integral that's a little different from what we looked at before, because there are two symmetric things that have to happen in this. One is the limits have to go off to plus and minus infinity symmetrically. So we're going to have a minus rho going to infinity and a plus rho going to infinity, and they're going to go off to infinity at the same rate. So we're going to have symmetry there. And we're going to have about the singularity at x equals 0, we're going to have r minus r and plus r. Just ignore the contour for the moment. It invaded the equation. So again, the r and the minus r is we're going to have a symmetry involved in that. So we're going to have two real integrals here that we want to evaluate. And we want to evaluate their sum, and knowing that the singular part that arises at x equals 0 is going to cancel if we make sure that they approach symmetrically. So now we pull a rabbit out of the hat. We've got e to the ix over x, and we say, let's consider e to the iz over z. This is not a substitution. I am not substituting x for z. I'm not substituting cos theta for z or anything. I'm saying, this formula is e to the ix over x. Let's consider e to the iz over z and see whether we can find something useful out of it. And it's going to turn out that we do get what we want, because the parameterization for e to the iz over z along this line is going to be e to the ix over x. And the parameterization for e to the iz over z along this line is going to be e to the ix over x. So we're going to recover one piece of this integral and another piece of this integral by considering this complex integrand over this contour. And that's a new way of doing integrals. That's not something that you've looked at before. So we consider this function, and we consider this contour where we integrate along here, hop over the singularity, along here, and out on a big circle around here, cutting into that formula. Well, there are no singularities whatsoever of this function inside that contour. The only singularity of this function is at 0, and that's outside the contour. So the integral all the way along this contour is 0. So that means we integrate from here to here, we add the integral from here to here, we add the integral from here to here, and we add the integral from here all the way back to here of these things, and we must get 0. So what we're going to do in a second is we're going to show that as we take rho going to infinity, the integral along the arc here is going to get smaller and smaller. The integral here is going to go to 0. So we'll be able to push that contour off to infinity and have no contribution from that. And then we'll be left with a contribution from here, and a contribution from here, and a contribution from here. And we're going to use that trick, the lemma of the principal value, to find out what the value of this is as we shrink the contours. We let r go to 0 symmetrically, and so we're going to pick up half the residue of this function here. So we're going to have this integral plus half the residue of this plus this integral plus 0 equals 0. And so we will have identified all four pieces of this, and we'll be able to solve for the sum of this one plus this one. Okay, cut.